Imagine time and space as a flexible fabric, akin to rubber or the net of a trampoline. Now envision twisting that trampoline net into a pretzel and suddenly finding yourself traveling backward in time. Have you ever pondered the mysteries that lie beyond our grasp in the vast cosmos? Prepare yourself for an extraordinary revelation that's about to shake the very foundations of our understanding of the universe. Get ready as the renowned physicist Michio Kaku unveils a discovery of monumental proportions, brought to light by none other than the legendary James Webb Space Telescope. This revelation may just rewrite everything we thought we knew, suggesting that time might not be as we perceive it. Are you intrigued to explore a mind-bending enigma that will challenge your perception of reality? The James Webb Space Telescope can be likened to the cooler, larger sibling of the Hubble Space Telescope. Launched on Christmas Day in 2021, this remarkable telescope now resides in space, shedding light on the deepest, darkest secrets of the universe. Think of it as the ultimate time-traveling device, equipped with incredibly powerful infrared instruments that allow us to peer into the distant past. But how does it accomplish this feat? Well, its unrivaled resolution and sensitivity enable it to detect ancient and faint objects that were previously beyond the reach of even the Hubble. We're talking about galaxies and celestial bodies from the earliest epochs of the universe, elusive entities that have remained hidden from our view until now. In essence, the James Webb Space Telescope is helping us piece together the cosmic puzzle, unveiling the grandeur of the universe, one infrared image at a time. Picture yourself wandering through an art gallery, admiring the magnificent displays captured by the James Webb Space Telescope, affectionately known as JWST. The scenes before you are awe-inspiring, with distant galaxies glimmering across the vast cosmic canvas. Yet, amidst the astronomers and cosmologists, there's an air of disbelief and consternation. It's as if they're gazing upon a Picasso in a room filled with realist paintings. The prevailing sentiment among them is one of astonishment. This is unexpected. But what's causing such a stir? What has unsettled their understanding of the universe to its core? While the official reports remain cryptic, the crux of the matter revolves around a cherished theory, the Big Bang hypothesis. This theory proposes that our universe originated from a colossal explosion roughly 14 billion years ago and has been expanding ever since, akin to a vast balloon. It has long served as the bedrock of cosmological knowledge. However, the latest images from JWST seem to challenge its validity, sending shockwaves through the scientific community. Imagine Alison Kirkpatrick, a seasoned astronomer from the University of Kansas, grappling with sleepless nights, questioning the very essence of her life's work. What's causing this widespread astonishment? Well, the galaxies captured by JWST are behaving in ways that defy expectations set by the Big Bang hypothesis. They appear too diminutive, too serene, too ancient, and their abundance is perplexing. Let's simplify the dilemma of too small. If we envision the universe as an inflating balloon, galaxies should not appear smaller as they move away from us. Instead, they ought to appear larger over time, as their light would have departed when they were closer. It's a peculiar yet fundamental aspect of the expanding universe concept. However, the images from JWST reveal galaxies that are comparable in size to those in closer proximity to us. It's akin to anticipating distant friends to appear as tiny specks on the horizon, only to find them standing right beside you, larger than life. Interestingly, these images reveal something quite unexpected. Galaxies appearing much smaller than anticipated, despite their greater brightness and mass compared to our own Milky Way. Surprisingly, they appear 2 to 3 times smaller than galaxies observed through the Hubble Space Telescope, HST, despite their impressive luminosity and mass. Moreover, these galaxies exhibit notably higher redshifts, indicating they're moving away from us at faster rates. You might find yourself thinking, well, that's peculiar. And you'd be correct, especially if you're considering the idea of an expanding universe. Back in 2014, some scientists noted this inconsistency while analyzing HST images. They observed that galaxies with redshifts up to 5 seemed to behave as expected in a non-expanding conventional space. It was expected that JWST would continue this trend, and indeed it has, even for galaxies with redshifts as high as 12. Put simply, the JWST images depict galaxies that appear similar in size to those nearer to us, suggesting that the universe may not be expanding and redshift could merely reflect distance. However, if we still adhere to the Big Bang Theory and the concept of an expanding universe, we're left with a puzzling conclusion. These distant galaxies must be incredibly minute to offset the perceived optical effects of an expanding universe. It's akin to imagining a grain of sand radiating the brightness of a spotlight. Consider, for instance, a galaxy dubbed GHZ2, spotted by JWST. Despite being significantly brighter than the Milky Way, it's estimated to be only 300 light-years in radius compared to the Milky Way's vast 50,000 light-year radius. Its brightness per unit area would surpass that of the brightest galaxy in our local universe by 600 times. Not only that, but its density, along with several other newly discovered galaxies, would be tens of thousands of times higher than those of the galaxies we typically observe. Now, as we delve into these diminutive and sleek galaxies, the very foundation of an expanding universe, and consequently the Big Bang Theory, begins to falter. This is precisely why these discoveries are causing such a stir among astronomers and cosmologists. Over time, images from the Hubble Space Telescope have presented a conundrum. They depict the presence of numerous galaxies, compact and robust, reminiscent of Mighty Mouse from classic cartoons. Deciphering these galaxies has proven to be a formidable challenge, and with the advent of the new James Webb Space Telescope, the puzzle has only become more complex. In an attempt to comprehend these peculiarly petite galaxies, theorists have proposed an analogy. It's akin to playing with a miniature toy car, a magical one that, despite its mere centimetre length, carries the weight of a full-sized SUV. They suggest that these microgalaxies collide over billions of years, merging to form the larger galaxies we observe today. It's akin to the toy cars colliding and metamorphosing into real SUVs. However, here's the twist. The JWST has closely scrutinized these galaxies and found no evidence of such cosmic collisions. One would anticipate these colliding galaxies to exhibit some signs of damage, wouldn't you agree? Perhaps appearing slightly disheveled or distorted, akin to a car post-fender bender. Yet, that's not the case. Instead, the JWST reveals galaxies that boast smooth, tidy spirals, akin to those in close proximity. There's a conspicuous absence of galactic dents and dings. In fact, a study aptly titled Panic underscores that there are 10 times more of these pristine spiral galaxies than theorists had anticipated. This is akin to encountering a bustling highway teeming with speeding cars but devoid of accidents. It deals a significant blow to the collision theory. With no traces of galactic mergers, the notion that these tiny galaxies expanded into their grander counterparts falls apart. If they didn't undergo growth in size, it implies they weren't small to begin with. Consequently, the anticipated optical illusion stemming from an expanding universe seems to be absent without this illusion. The concept of expansion loses traction, leading to growing apprehension among proponents of the Big Bang. The emergence of these small, polished galaxies suggests that the universe may not be expanding. And if it isn't, the Big Bang Theory suffers a significant setback. Additionally, there's another aspect to consider: the age of stars. The Big Bang Theory proposes that everything originated from a monumental explosion. However, if these galaxies existed prior to that event, it would imply that the Big Bang never occurred. This could significantly alter our understanding of the universe's beginnings. Think of the James Webb Space Telescope as a time travel device. As described by Michio Kaku, it has the capability to peer billions of years into the past, capturing images that unveil the universe's early history. This remarkable instrument doesn't capture photos in our familiar visual spectrum. Instead, it focuses on the infrared, revealing the colors of galaxies so remote that they are beyond the reach of our unaided eyes. Now, here's the intriguing part. These colors aren't merely aesthetically pleasing, they narrate a tale about the stars' ages within these galaxies. Young, energetic stars emit vibrant blue hues, while their older, cooler counterparts, akin to our Sun, radiate in shades of yellow and red. By analyzing these colors, astronomers can estimate the ages of the stellar populations within these distant galaxies. According to the Big Bang Theory, the galaxies observed farthest away in the JWST images offer a glimpse of the cosmos around 400 to 500 million years post the universe's inception. However, some of these galaxies appear to host stars that surpass 1 billion years in age. Now, if you're familiar with the Big Bang Theory, you'll recognize this as a significant conundrum because nothing should predate the Big Bang itself. Another anticipation, if the Big Bang Theory holds true, is that as we peer deeper into space, essentially peering further back in time, we should observe a diminishing number of galaxies until eventually encountering a period where none exist, a cosmic dark age, so to speak. However, reality appears to tell a different tale. It appears that galaxies as substantial as the Milky Way were already prevalent even just a few hundred million years after the proposed Big Bang event. The latest images reveal something astounding. There are at least 100,000 times more galaxies at high redshifts than previously estimated, exceeding expectations by more than tenfold. This raises the crucial question: how could such a vast number of large galaxies emerge within such a brief time frame? The likely answer: they probably couldn't, at least not within the confines of the Big Bang Theory. Hence, these discoveries are shaking the very core of our understanding of the universe. Adding to the intrigue, recent findings suggest that the Big Bang Theory might be missing the mark on numerous fronts. Surprisingly, it's been found to inaccurately predict 16 different outcomes. Yes, a whopping 16. The only prediction it gets right concerns the abundance of deuterium, a variant of hydrogen. But that's not all. This long-standing theory overestimates the quantities of helium and lithium in the universe, and it struggles to explain the existence of the colossal structures we observe. According to the theory, these structures simply shouldn't have formed in the time since the universe's inception. Furthermore, the theory encounters hurdles when attempting to predict the density of matter in the universe. And here's an intriguing twist. Remember those purportedly non-existent asymmetries in the cosmic microwave background? Well, it turns out they do exist, revealing a cosmic plot twist of sorts. So, where do we stand? Enter the James Webb Space Telescope. This cutting-edge technological marvel holds the potential to unravel these cosmic contradictions. While these discrepancies may seem like minor details amidst the vast tapestry of cosmic knowledge we've amassed, rest assured they are anything but insignificant. Each small discrepancy acts like a piece missing from our cosmic puzzle, obscuring the grand picture and leaving us with an incomplete grasp of the universe's essence and origins. These aren't just any missing pieces. They are foundational elements of our comprehension of space and matter. These irregularities cast doubt on everything we believed we knew about how the cosmos came to be and evolved. They challenge our understanding of cosmic structures and the very fabric of space-time, which underpins our grasp of universal expansion, gravitational waves, dark matter, and even the ultimate destiny of the universe. Consider this. If the density of matter isn't as anticipated, it could reshape our understanding of galaxy formation and evolution, along with reconsidering the role of dark matter in these processes. Similarly, the unexpected variations in the cosmic microwave background might alter our understanding of the universe's initial state and the pace of its expansion. What's more, These inconsistencies even reverberate into our comprehension of time itself. Currently, our perception of time is intertwined with the universe's evolution since the Big Bang. If the Big Bang theory falls short, we may need to reassess our notions of time, its passage, and its connection to space. Ponder this possibility. These discoveries might usher in a paradigm shift in how we perceive space-time compared to when Einstein introduced his theory of relativity. We might stand at the precipice of a fresh comprehension of the cosmos, necessitating the recalibration of our cosmic timepieces and the redefinition of our cosmic orientations. The universe never fails to surprise us, does it? Let's delve into a profound question. Is time truly a fundamental aspect of reality, or merely a construct devised by humans to delineate between past and present? Consider this intriguing theory. Time is merely an illusion shaped by our human perceptions and memories. According to this concept, every event, past, present, and future, is unfolding simultaneously. It's a notion that challenges our conventional understanding. Let's explore further. We tend to assume that time flows inexorably forward. However, the laws of physics don't necessitate this linear progression. They remain consistent whether time moves forward or backward. Take, for instance, the Big Crunch theory, which proposes that as the universe contracts after expanding, time could potentially reverse its course. As the universe contracts, it heats up, akin to a reverse Big Bang. But what lies beyond the Big Crunch? It's a question that has intrigued minds across the ages. Some hypotheses suggest a new universe might emerge from another Big Bang, while others speculate our universe could reappear elsewhere entirely, akin to a cosmic bubble bursting into existence. There are even theories positing that this cycle might repeat endlessly, giving rise to myriad universes. This intriguing possibility of time oscillating between forward and backward motions has led some scientists to a bold assertion. Time, as we perceive it, is merely a human construct. They argue that we inhabit a block universe, where space and time are intertwined, a concept supported by Einstein's theory of relativity. In this model, all events, regardless of temporal placement, possess coordinates within the four-dimensional space-time continuum. What does this imply for us? Essentially, it suggests that every moment, past, present, and future, holds an equal footing in reality. The past and the future persist, existing somewhere within the fabric of space-time. MIT physicist Max Tegmark eloquently articulates this notion, suggesting, we could perceive our reality as a three-dimensional realm where events unfold over time, or a four-dimensional expanse where nothing transpires. Everything simply exists. If we subscribe to the latter interpretation, then time becomes an illusion because there is no real change. All aspects, past, present, and future, permanently coexist. It's a concept that might initially boggle the mind, yet isn't it enthralling to contemplate such profound questions? It underscores the unfathomable magic and enigmatic nature of our universe. Then there's Julian Barber, a British physicist with a captivating viewpoint on time. He envisions our reality as a series of discrete now moments, akin to individual snapshots in a photo album. Picture flipping through this album, where each photograph represents its own distinct now. That's essentially how Barber perceives the universe. Barber posits that our perception of the past is merely a construct of our brain's memories. Essentially, we believe in the existence of the past because our memories attest to it. According to Barber, the concept of the past might well be illusory. He delves deeper into this idea through his spatial theory, wherein each now moment occupies a specific location within an expansive landscape, whimsically dubbed Plutonia. Every point within Plutonia signifies a distinct now, and this landscape adheres to precise mathematical principles, rendering it timeless in essence. This perspective harkens back to a more familiar figure, Albert Einstein. Einstein's theory of space-time serves as a cornerstone of our current understanding of the universe. However, its implications and our comprehension thereof have spurred profound inquiries. What if Einstein's concept of space-time was flawed? Might discarding it entirely offer us a clearer understanding of the universe? This ongoing cycle of inquiry and discovery epitomizes the progression of science. Looking back through history, we witness how this process has unfolded over time. The geocentric model, which positioned Earth at the center of the solar system, held sway for over a millennium. Then along came Nicholas Copernicus, proposing a revolutionary notion. Earth is just one of many planets orbiting the Sun, ultimately supplanting the geocentric model. Following Copernicus, Isaac Newton introduced a fresh perspective on gravity, suggesting that all objects with mass exert a gravitational force on each other. In this framework, Earth orbits the Sun and the Moon orbits Earth due to their mutual gravitational attraction. Newton's gravitational theory dominated for roughly 3 centuries until Albert Einstein unveiled his general theory of relativity in 1915, reshaping our understanding of gravity and spacetime. Einstein proposed that massive objects like the Sun cause a curvature in the 4-dimensional fabric of spacetime. Earth moves along this curve, resulting in what we perceive as gravitational pull. The shift from a geocentric model to Copernican heliocentrism and from Newtonian gravity to Einstein's general relativity underscores the evolving nature of scientific comprehension. Despite the enduring strength of Einstein's theories today, physicists persist in questioning, investigating, and pushing the boundaries of our understanding of time in the universe. Einstein's theory of spacetime has endured for over a century, triumphing over numerous challenges. A pivotal moment arrived in 2015 with the detection of gravitational waves, a significant validation of his theory. However, no theory remains impervious to scrutiny. A notable challenge arises when Einstein's general relativity, encompassing the concept of spacetime, encounters the realm of quantum physics. These two realms appear to operate on distinct principles, posing a formidable conundrum.